Hello. Super. So I'm Ainar Drews. I'm the Technical Coordination Manager at AIMind, and I'm going to talk a little bit about the opportunities created by artificial intelligence in dementia research and diagnosis. I thought I'd just introduce myself really quick. As I said, Technical Coordination Manager. And I work at the University of Oslo at the section for research platforms, which is where we save the data that Ira just mentioned at the Services for Sensitive Data called TSD, as I mentioned. And although I work in AIMind now and hang around a lot of neuroscientists and lots of other people, my background is actually in astrophysics, which is somewhat of a outside view on all of this. But I did work with some AI in astrophysics because it is everywhere, and that's sort of what I bring to the table here. But so normally I'm in a lot of meetings and Zoom calls, and I talk with a lot of different people in AIMind, and they all have a very different background. So I talk to software devs, AI researchers, academic researchers, and medical clinicians. I am tired a lot because they do speak quite different languages. They talk everything from neuroscience to complicated software development that I'm not that familiar with, clinical terms, and lots of other stuff. But today I will be talking and trying to make approachable from sort of synthesizing everything in AIMind when it comes to the AI development, and talk a little bit about our actual goals and the opportunities, as I mentioned, what we want to create in our research and diagnosis of dementia. And it's going to be from a slightly technical perspective. So for those that aren't experts in AI, don't be worried. And I'm going to say sorry to those who are experts in artificial intelligence and in this field, because it is going to be a broad overview. So the why. Why are we doing this? And you might have guessed something from our name. We are trying to use artificial intelligence to study the mind. Maybe AI brain might be more accurate since we are looking at the brain, but it doesn't roll off the tongue quite as nicely. But why do we actually use AI and not other more standard stuff that has been used in the past? So artificial intelligence is not just hype. It might be why you're here right now. You heard AI, and that's pretty cool and has been in the media a lot. There is a lot of the hype, but it's not just AI images with too many fingers or somewhat creepy chatbots. It does actually show quite a bit of promise, and there are real results, and especially also in the medical field. And to just jog the imagination a little bit, there is more efficient screening of blood cells for malaria infections, detecting falls in elder care. The detection and risk protection for breast cancer is a very active research area. And you have chatbots that might actually also play at therapy, however you might feel about that one. But so there is a lot to gain from using AI, and especially in dementia, there's also stuff that we can do. But when it comes to AI, I find that a lot of people don't actually really know what I mean by AI when I talk about it. And so I thought I'd just sort of introduce the hierarchy here of what is actually artificial intelligence before talking about it a little bit more. So artificial intelligence, for those who are sort of a little bit intimidated by the term, it is literally just a catch-all term for any sort of thing that you do on a computer that is sort of similar to what humans do when they think about stuff. So it can be as simple as doing a sort of interpolation of points in your graph, and as long as you do that automatically, congratulations, you've technically done artificial intelligence. I wouldn't show up to a conference with that, but it is something. Machine learning, you might have also heard, that's sort of the earlier term that's been a little bit hyped, whereas now it's AI and deep learning. But machine learning is really just a subfield of AI. And usually it's characterized by using algorithms that are unsupervised or reinforced. You don't have to care that much about these terms, but usually it's a little bit more classical, and you'll use statistical methods and more sort of traditional algorithms. Deep learning is the hot new stuff, and that's also behind a lot of the push and the new technological developments that are more recent, and is again a subset of machine learning. And these algorithms are sort of an attempt to mimic the way that the brain processes information through something called neural nets. And these are deep neural nets, and that's where the name deep learning comes from as well. So a little bit, so machine learning, again, as I said, it's pretty much any algorithmic implementation of artificial learning, and is often statistical in nature. So for example, on the right here is what's usually called the simplest of machine learning algorithms, the k-nearest neighbor. If any of you have ever touched machine learning, you've probably seen it. And in that instance, for example, you've got an unknown point in your data, and you just look at the nearest neighbors, and whoever it is closest to that you already know which type it is of, you just say, okay, this is probably going to be a red triangle if you look at the 3 closest neighbors, or maybe it's a square, and then you look at the 5 closest ones. So again, you have to check your parameters and so on, but still fairly simple. The question of what output you get from a given input in machine learning is usually quite clear, at least on a theoretical level, because you can look at the code, you know what it does in a sort of deterministic way, and it's usually more knowable or more easily investigated than for deep learning at the very least. Deep learning, on the other hand, much simplified, and I'm not going to go into details here, is, again, technically just a subset of machine learning. Deep learning is machine learning, it's just a specific case of it. And it tries to mimic the neural network of real brains in that sense, so neural network learning. Deep learning consists of neural nets with multiple hidden layers, as they're called, again, hence deep learning. It consists of a layered structure of algorithms that you feed your data through, and each node represents a feature or something that the deep learning algorithm is taught on. And this is a very simplified sort of schematic of it, where you have an input layer where you put information in, it flows through your hidden layers, and it comes out in the output layer. And these sort of like, you might have heard about it, there's this feature called the black box problem when it comes to deep learning, where in your hidden layers, you can't actually really know what's going on as you feed data through it, and you don't actually know what you get out until you look at your output. So what you can do is you put in input, your deep learning algorithm sort of learns, in quotation marks, it's not like a human learns, and then you get something in your output layer, and then you inspect what you get out, and hopefully it's useful. And the sort of main principle is that you feed information in, different features will be reinforced in the different nodes of the neural network. Again, for those of you who study the brain, that might sound somewhat familiar. And then each of the different nodes becomes set in a way and learns different features of whatever you're trying to teach it. And to sort of show this off a little bit very much symbolically, here, for example, you've got sort of the different nodes or layers of a deep learning network that is trying to identify different kinds of animals. Here it starts out just like with lines, like where are the borders between the animals, the background, contours, and in the end it gets a contour of the elephant, and it characterizes it as an elephant. And a little bit more advanced, for example, in image recognition, your deep learning algorithm, different features that it might learn is like simple stuff like colors and shades, then it moves to edges and textures, and then in the very end it manages to recognize specific objects like person on a bench or grass next to a path. And when it comes to deep learning, most of it is actually about the data. The data is one of the most important parts when it comes to deep learning, because deep learning is very computationally expensive. You have to run your algorithms a lot of time over a long period of time, so weeks, months for the most complex ones. And they're sort of slow learners. These features that you are trying to set in your deep learning algorithms need constant reinforcement through your training. And it's sort of like a toddler. You don't really think about it, but as a toddler grows up, they see millions of different things in the world. They see lots of different chairs, lots of different tables, lots of different faces. And so it might seem a little bit unintuitive how much or for how long we have to teach these algorithms, but it's the same thing for a person in a sense, even though it's not the same again. But as I also mentioned, they require very large amounts of high quality data. So it needs data that is labeled very specifically. You can't just show it images that are grainy and blurry and not labeled properly. You need a nice picture of a table, and it needs to be labeled as a table for it to actually recognize it usually. There are some ways around it, but that's the gist of it. And as I mentioned, much of the revolution in AI is actually a result of access to huge amounts of data nowadays in the digital age. Because nowadays you actually have the internet, and a lot of these large corporations with like the AI companies like doing Stable Diffusion and the others, the ChatGPT and stuff, they scrape the internet for basically all of human knowledge and manage tag it and then train their algorithms on it. For example, this sort of image that is a little bit outdated now, created by Stable Diffusion, uses a data set of 5 billion image text pairs in the Leon 5B data set from Stable Diffusion. And it still can't get the hands quite correct, even though it is an astronaut riding on the moon. But they've gotten better at this point because they fed it more data as well. But AI minds AI. Why? Why does AI mind actually use AI? We will have a lot of data given our field, so that sets us up well for the case of deep learning at the very least. We've got 1,000 participants with 4 recording sessions each with a variety of data, which includes EEG scans, biomarkers, cognitive scores, and social demographics. And deep learning in particular shines when coupling different correlated data types, which is one of our goals to actually investigate. Our data is high quality, ethically collected, stored, and processed, as we mentioned before. And we have assembled a unique mix of expertise in neuroscience, AI research, software development, ethics, and more to actually take advantage of it and do so in an ethically sound way, which is not always the case when you read the headlines when it comes to deep learning development. And I'm going to sort of restate our goals in AI Mind very much focused from an AI perspective. And goal 1 is really to find features in the brain that indicate whether someone living with mild cognitive impairment will progress to dementia. We want to understand dementia at a more fundamental level so that we can find treatments. Or what causes dementia, sort of, very much simplified. Goal 2 is more specifically be able to predict whether a specific person diagnosed with MCI will progress to dementia. And this will enable clinicians and people living with MCI to make informed choices about treatment options. Or will you get dementia? And goal 1, translated to the AI tools that Ira already mentioned, is that we want to use our large data set of EEG and MEG readings of people diagnosed with mild cognitive impairment and find features in these recordings that correlate with people progressing to dementia. And then analyze these features to find the actual changes in the brain. And this will be the connector tool. The connector tool is going to be primarily aimed at researchers who aim to understand dementia and its effect on the brain. And goal 2 is translated into another tool, and this will be using AI methods to be trained on EEG, MEG, cognitive, social demographic biomarkers, and analyze them all together in one data set so that inferences from one data type can be used with inferences from other data types. And this will hopefully then enable us to actually predict whether a given individual, which we then compare to our already taught data sets or taught algorithms, whether or not they will progress to dementia. And we'll also use insights from the connector in this tool. And here we want, of course, high accuracy and low uncertainty and robust values for these predictions. And this will be the predictor tool. And this one is mostly going to be targeted at clinicians who want to provide a prognosis for their MCI patients. That means that they can then make informed decisions together about potential treatments or mitigations plans. And this is, again, a graphic over the entire concept, where we have the EEG data coming in first for the connector and where we analyze everything. This gets fed in turn into the predictor together with genetic and cognitive data. And then in the outcome, we both have a better understanding of both dementia in the brain and have a method to predict whether or not someone will progress to dementia or not. And circling back to the very beginning, what big opportunities does this actually translate to? And this will, of course, as I stated, give us a deeper understanding of the brain and how it changes with dementia. And this gives us new opportunities for new research and insights. And of course, AI in particular can uncover unintuitive things that a human would not uncover from data at a glance, because it specifically can sift through details that you wouldn't notice, that aren't classical features in the normal sense from normal clinical practice, which AI is very nice at actually detecting. And once we've actually identified it, we can follow up with actual study by real humans again. And this is hopefully going to lead to a beyond the state-of-the-art diagnostic tool and to predict whether or not someone goes on to get a dementia diagnosis with an above 95% accuracy and high confidence. And of course, as mentioned already, today we can only provide a statistical number. You've got about a 50-50 whether or not your goal will be progress. See you again in 5 years, which is simply not good enough and not very heartening. So, and of course, the sort of big headliner is earlier interventions, more targeted treatment. And that's what we hope to achieve in a nutshell. Thanks.